afternoon, everybody. Welcome to the NC-CAV seminar series. Today's speaker is Dr. Shih-Chun Lin. He's an assistant professor with electrical and computer engineering at North Carolina State University. He's the director of Intelligent Wireless Networking Laboratory. He received his PhD from Georgia Institute of Technology in 2007. And his MS degree and bachelor degree from electrical engineering from National Taiwan University. He has published more than 47 peer-reviewed papers, holds 10 US patents, and has received numerous awards. He has been working with several collaborators, including and with different agencies, including AFRL, Cisco, and so on software-defined networking and software-defined radio architectures. He, in particular, is the co-lead under Trust 2 of the NC-CAV Center, which is investigating the impacts of, the infrastructure needed for deploying of CAVs. His research interests include 5G and beyond architectures, mobile edge computing, machine learning techniques, and mathematical optimization and performance evaluation. And today's talk is on machine learning enabled and ultra low latency connected transportations. Without further ado, please join me and invite Dr. Lin for today's talk. Thank you.
Thank you, Ali, for the generous introduction. Good afternoon, everyone. Thank you for attending my presentation. And as mentioned, the title of my talk is 6G Industrial Verticals, and I will mainly focus on how to establish ultra-low latency connected transportation. Okay. So first of all, when we talk about 6G, let's look back about what's the current 5G wireless systems. So 5G is very different from the 4G, as you might aware. It asks the data rates need to be 100 times more as compared to the 4G LTE system. And not only that, they also consider different types of metrics that haven't been considered in the 4G era. So such as we need to support connections for billions of things and peoples to set up the scalabilities. And also another interesting metric is about the latency. Okay? So for the 5G, we try to reduce the latency for the end-to-end transmissions down to 1 millisecond. So that's kind of the overview pictures for the 5G. And currently it's like second phase of the 5G. So I guess you guys might already heard some of the technologies from there. Then how about 6G? Okay. Like 6th generation mobile system. So the evaluation from 5G to 6G, as you can see, I included this figure here. There is not much difference between the key performance indicator. So the 5G already cover a very wide of KPI, and the 6G also focus on that. But the major difference is like the 6G asks for more strict performance, such as you need to have a better system capacities, like 50 times more for the peak data rate. And also for the 6G, they consider like the jitter and also energy efficiency. In other words, more strict requirements are needed for the 6G technology. And it will be enabled by major structures, as I show here, like you need to have the new designs of the last mile transmission, such as you need to have new spectrum usage, become like more upper frequencies such as the millimeter wave or even up to terahertz communications. Also, you need to have more intelligent designs for your network architectures. And of course, for the 6G network, is expect not only it can connect the terrestrial environments, but also beyond terrestrial is also the considerations or the focus for the 6G system. So that's why you can see there are a lot of like emerging areas into these new topics. So in other words, roughly every 10 years, a new generation will release, like from 4G, there is 10 years to the 5G to 2020, and we expect like 6G, some of the technology will land down like around 2030. So this figure also show, or like from these papers, also show the similar ideas as I just mentioned. The 5G and 6G, they all care about these multi-dimensional objectives. It's just the 6G need more strict performance for the objective. And on the other hand, the 6G also enable new industrial verticals. Okay, so for this new next generation wireless systems, it is not only focused on the cellular communication, but also how can you deploy these ICT or digital innovations into different domains. To summarize, the 6G directions based on the limitations of 5G, and there are three main pieces that has been focused on both by the academia people and also the industrial engineers. So the first one is the physical communications. How can you increase more powers, increase more bandwidth, yet lower power for my last mile communications? The second one is a new area, or it's still ongoing. That is the industrial verticals. How can you support different type of industrial applications, such as the e-health, remote surgery, automatic vehicles coordinations, and also smart factories. So that's all are very active nowadays. And the third portion is how can you include this machine learning or AI intelligence into different levels of the system architectures, like you can increase a better intelligent design for the RF end to boost the data rate, and also this machine learning can also help the system orchestrations to provide a better upper layer performance. So that's the three main you can think about like research questions or research areas that people are jumping in this domain. So with this understanding today, I will talk about one of the critical applications in this 6G system. That is the smart and connected transportation. So how can you establish a smart and connected transportations for massive autonomous vehicles, or CAV, connected and autonomous vehicles? Then I will mainly introduce some of our current work. We call it SDVAC, the software-defined computing architecture. That's the new architecture designs that we based on our previous knowledge of 5G, mobile edge computing, machine learning, to build up this new type of infrastructures for the future driving paradigms. And I will give some details like how can we establish this multi-scale computing infrastructure, and how can this infrastructure can support ultra-reliable low latency communications. And of course, I will also present some of the test-bed development and experimental verifications with this regard. And finally, I will use 2 or 3 slides to talk about other ongoing 6G industrial verticals that also has been researched in my lab. So first of all, regarding these autonomous vehicles, there are different types of realizations for these autonomous vehicles. As you can see, you can either have this fancy helicopter-wise vehicles that can help the CAV communications, and also you can also install some of the wireless connectivities above the vehicles to make sure these vehicles can now connect to the environments and can help its autonomous driving paradigm. So the idea is from the driving assistant to autonomous driving. So nowadays, you might already see some of these fancy functions that can help the drivers to drive when they are on the road or in the highway. So they are the main task is still operated by the human, but there are some sensor devices or like onboard sensors, and also some of the intelligence has been deployed nowadays. But our target is to make like the car drive by itself, like SL to the level 4 or 5. So one of the idea is if there's a car coming to the intersections, how can it aware there is another car is trying to take right turn, and in such a way it can stop, slow down its speed to prevent a crash in the intersections. So this idea is not only a single sensor device can fulfill these requirements, but you need to have multi-sensors, maybe in multiple cars, and also the environment support to perform various tasks for this autonomous driving. So in other words, the myth of this autonomous vehicle is that the full autonomous operations is enough. So like the Tesla or these car vendors, they also try to make this car very smart, but there is not much considerations about like this connectivity. So the reality is that the massive automation is much better with this connectivity support. Means you have the connections between different cars and also the infrastructure. So one of the example is like if you have the AI, if you have a very smart autonomous vehicles, but if you don't have this wireless networking or this connectivity supports, it's very easily to cause some tragedies, especially in very severe environments, like in the nighttime, and it's very dark. Your sensor even like it's not like workables, or maybe you get different results from different sensors, and it can make the misunderstanding of the intelligence on your car. So in other words, the single engine AI with only onboard sensors does not satisfy our need. So there is still a long way to go to fulfill this autonomous driving. So some of the ideas from the work is like maybe we can including the connectivities and also the sensor infrastructure to make like a smart and connected infrastructure. In other words, we can including some capacity or potentials from this roadside unit or like access points on the roadside. They can help to exchange the information maybe in advance, and then to report to the drivers what will happen in the next 10 moments. So in other words, if we can support this sensor sensing device or like connectivities, actually we not only can provide a better coordinations between massive CAVs, but also we can support different automation levels of the cars. So some of the cars might not have this connectivity capacities, but if we put this infrastructure support, actually they can also support some of like the conventional cars, like the one we drive nowadays. And to the extreme, if we can build up these smart and connected infrastructures, actually we even don't need this traffic light, or this traffic light intelligence can be eliminated because everything is coordinated perfectly, and the car will know when to stop and start the engine. So that's our vision. And some of the industrial partners also focus on this area. They starting consider the connected vehicles, how to use this V2X, the vehicular to vehicle to everything use cases. So such as this here, like from the direct communications between the cars, actually this connectivity can help a lot to recognize and inspect environments or inspect events when the car is driving on the road. So from this direction, the Qualcomm is a big player, as they already have a very good support from the cellular infrastructure. So they try to pursue this C2V2X. That means the cellular to vehicle to everything direction. So this figure shows like two of the technologies that has been adopted for this car connectivity or wireless communications between cars. The one is the basic one. It's called IEEE L2.11p, and I will talk more in the later slides. So it's just a basic technologies that trying to connect the cars, maybe in the adjacent areas, and there is not much focus on the safety concern. So I just want to be able to talk to some of my neighboring cars. That's it. And on the other hand, the other direction is if we have this cellular support, actually we can use some of the development from the cellular systems like 4G, 5G, 6G to increase or to help the build up for this autonomous driving case. So that's will provide enhanced safety to a very good community or public safety cases. So it can be summarized briefly into these slides. So the L2.11p, or we know as the DSRC, the Directed short range communications, or sometimes we call it WAVE, because it's a wireless. It's the first time that people want to use this wireless access into the vehicle environments. So as you can see here, they try to support limited communications between the cars, because that's the first versions that people think about. Okay, we can use this wireless networking to help our transportation environment. And our focus mainly is if we have this cellular support, actually we can support a larger transmission range from the cellular infrastructure, and we can also support the reliabilities as well as the low latency. So that's the main focus and also the current trend for the US DOT. So how can you transfer from this more like AHA connections to the cellular-based communications? So some of the latest progress from the C2V2X is for the release 16. It's around like 2018 timeframe. Several requirements for this next generations. Next generation is the V2X applications has been discussed in this release 16. And they also consider if we have 5G NR, NR means a new radio. If we have this 5G new radio, how can it support the V2X communications? And in a way, how can we enable the enhanced version of the ultra reliable low latency communication? Okay, now, so that's in the release 16. It's still ongoing. And for the release 17, like the new one for the 3GPP standards, the release 17, as I show here, is sometimes called the next phase of the 5G standards, and is expected to finish in the second phase of 2021 and 2021. And the main ideas for this vehicle environment is based on the release 16, and it tried to enhance the sidelink capacities from the conventional vehicles to vehicle communications to vehicle can also contact or communicate with these smartphones or even pedestrians, more like the battery powered devices. And it also focused on this public safety issue. So with this understanding from the progress of this wireless networking and communications, actually the idea is how can we push the SAE levels to the high and full automations for massive CAV users. So that's why the idea of the DSLC can kind of help to push these autonomous driving paradigms, but the main idea is still needing this cellular support to enable these mission critical and ultra low latency services. However, one of the critical issue here is the current, how can we support the phase mobile networking to meet the end-to-end latency down to 1 millisecond for large scale reliable deployment. So how can we set up, how can we literally reach to these end-to-end transmissions for this 1 millisecond? Because once the communication has fulfilled, there is still some operations for the control or even some mechanic operations need to operate by the cars or the infrastructure. So that's why we try to shrink the time that you needed for this last mile transmission. So it's very hard to achieve this 1 millisecond timing. And the main issue is the current or the conventional vehicular network paradigms still focus on this communication protocol-based networking. And the bottleneck is like it can support only up to 20 to 100 milliseconds. So it's more like 20 to 100 times more delays that we can get or as compared to what we expect. So here I list some of the reasons why we cannot shrink the delay for this communication paradigm. So the easiest idea is like when they adopt these wireless technologies into the vehicle environments, they just borrow and play, means they don't dedicate to the designs for the vehicular environments. So we still have very cumbersome that you use for the internet or even like a wireless 5G communications. We still have this very cumbersome protocol stack and optimizations, and we hope that can also run in the vehicular environments. So that's the key point that we cannot shrink this delay to 1 millisecond level. And the other idea is the current state of the art is still focused on the data center computations for the wireless core network infrastructure. And if that is also borrowed from the cellular system, it's not that matched to the vehicular environments. So some of the idea is to use this vehicular edge computing. It's like instead of transmit all the data back to the cloud, if we have some computing agents in the local end, such as around the roadside units, and if they can already perform the computation process, they actually can react much faster to the vehicles and then to help to shrink this delay. So the idea is there are some cars running on the road, and we have these access points as the roadside units, like all can be sensors on the traffic lights, so they can collect the information from the vehicles, and then they will pass in this information to the local transmission units, and the transmission units or like these anchor nodes can calculate the results and then react to the vehicular environment in a very short period of time. So that's the kind of the ideas help us to address this 1 millisecond requirement. However, there is still some challenges or open issues from this VEC, the vehicular edge computing, such as how can you address very mobile, unreliable wireless links, because now your car is driving, if it's driving in the highway, how can you make sure you can always provide continuous and reliable connectivities for the cars? And sometimes when we say, okay, we bring out this cloud computing into the edge computings and help us address 1 millisecond, sometimes we will overestimate if we don't dig into the real environments. So some of the overestimate capacity for this edge computing is like we might forget, or we might avoid to consider these overheads, like how can you set up these local computations, because there will be multiple of them on the roadside cases. How can you set up the scheduling, or how can you set up the cross node consensus if there are multiple local computing units? In other words, you still need to have a pretty good, nicely performed network infrastructure to help this VEC idea. So one of the latest idea is called the SDN. So the SDN is a scheme that can help to provide the global optimal control. The idea is we now, for the SDN, they centralize the control plane into an agent, and they let these data forwarding devices only consider the data forward. So all the network intelligence can be centralized or logical centralized into the controllers. And in such a way, you can have a flexible and global control for the entire infrastructure. So that's the ideas comes from the computer science, and we already using this idea into this wireless environment. So this work is around like 2015 to 2018. So we try to bring this global control capacities into the wireless infrastructure. So in that case, we build up called the software. We can softwareizations the radio access network and also the core network part, so that centralized controllers can have the global view of the entire infrastructures, and they can provide the control and monitoring timing. So that's where we have our know-how to help us address this vehicular edge computing issue. Our idea is for this next generation wireless networking architectures, we first have this software-defined infrastructure help the controllers have the centralized view of the infrastructures, and also it can program the data forwarding elements. And our current work is not only we consider this software-defined infrastructure into the wireless domain, but how can we also incorporate or integrate this intelligence into the wireless domain? So that's why we call it computation-based wireless edge networks. So now we focus on the edge devices that has computing capacities for your environments. And instead of focus on the computation protocol based, now we focus on how can we use the computation to address the need for like your QoS, the quality of service, such as the 1 millisecond requirement. So we currently have two realizations. One is the one that I will present today. How can we use this computation-based wireless edge networks into the vehicular edge environment? And the other one, we also have a very needy idea, a very precise idea to use this idea into the smart factories. And if you are interested, feel free to read these two papers. So today's focus is how can we use this software-defined infrastructure and combine with AI for our vehicular edge computing. The idea is in these environments, we have heterogeneous network architectures, meaning we have the edge node that has the as the anchor nodes that has the edge server can perform some machine learning or some data processing in the local end. And also don't forget, we still have some support from the cellular system, right? So the cellular system, maybe these high power nodes, they can support a wide range of the transmission of communication ranges. And of course, we still have the cloud layer, okay? So it's more like the heterogeneous network, meaning it's not just the edge network, but also you need to consider all the capacities from the infrastructure perspective. And we call it the multi-scale computing environment because now you can consider the computation on the devices, means the computation on board, OBUs, on the cars, and also you can consider computations on the edge side and also the cloud side. So literally, you need to have a very good platform that can understand all the infrastructures and can scheduling all these computation resources, communication resources, or even like the machine learning tasks well. So our idea is we introduce these distributed computing architectures. We focus on how to perform the computations. If you have multiple anchor nodes among a large vehicular environments. And this anchor node, as I mentioned, can collect the information from the roadside access points. So the idea for this structure is we offset the communication to computation. So as you can see later on, we just apply the basic, very intuitive or sometimes trivial communication scheme called the open loop communications. In this very trivial scheme, we can shrink the delay to a very short period of time, but the drawback is there will be some collisions there. And our idea is we use the computation to recover the collide packets to correct the information. From that ideas, we reduce the latency and we can preserve the reliability. In short words, we exchange the communication with the computational nodes. And we can also, since we build up these SDN infrastructures, we can easily have the computation offloadings between the local end and the cloud end, since we already did that for the software, for the cellular infrastructure. So that's kind of like the advantage for this SDVAC. And here shows some of the details for this SDVAC. So we need to establish a very ultra reliable low latency data plan, means as I mentioned, we adopt this very basic open loop transmission instead of the closed loop that you will need to go through the three-way handshaking or even four-way handshaking. So we just once the vehicle has the information to transmit, it just directly transmit. And even though there will be the data will be collide at the receiver side, our receiver access point have the machine learning capacity to recover the error and to still preserve the reliability. So that's the data plan designs. And we also consider, since we have multiple edge node, or we call the anchor nodes, so how can you set up a scalable computation-enabled control plane? And the third pieces is how can we support our required QoS, such as the latency and reliability. And we use the virtualizations, or sometimes the people know as the network slicing, to slice the resources. Now, in this case, it's multi-dimensional resources. How can we slice the resources to support the application requirements? And the last piece is that since we enable these distributed computing infrastructures, actually the big data or this big data approach can seamlessly integrate into our platform. And I will also show some of the examples how can these big data applications to support like the privacy learning, privacy preserved learning, or like the security framework. So there are so many details, but I don't think I can cover all of them during these seminars, but I will tell the main key ideas, and if you are interested, feel free to reach to us and we can talk from there. So the main idea in this is showing in these pictures. So we have the data plane, and that including the CAV cards, the access points, and these access points will collect the data information into the local anchor nodes. And these anchor nodes need to support these virtual clusters for network slicing, and they have these distributed SDN controllers to make a consensus of the network infrastructure for multiple anchor nodes. And also they support the edge computing. And for the backhaul, they can communicate with this core network. Like there's cloud computing agents there. So that's kind of the entire structure. So the idea is these open loop transmissions help us to get this 1 millisecond transmission. Let me show you in one of the figure. So conventionally, you will think about, okay, there's a base stations, and one base station, it has its own coverage, and it supports all the control and signaling for the users around its coverage. So instead of using these schemes, we try to use these virtual cell ideas. So that means we can now use multiple base stations to support a single user's usage. So in other words, if this user have the data to transmit for the uplink transmission, it's just broadcasting the information, and the nearby access points likely will receive multiple replicas from this broadcasting, and since all the information will be aggregated to the local anchor nodes, and these anchor nodes can perform machine learnings and to adjust if there is some collide within the last mile transmission. So our idea is, instead of trying to make these handshakings between the base stations and the cards, now we just let the card transmit, and everything, all the computation will be addressed by the infrastructure. And in this case, we can not only address the current transmissions, but through this machine learning on the road side, we can even predict what will happen or what's the next time slot associations between the cars and the infrastructures, so that we can do the proactive access for the cars. So that's the ideas for how can we perform these virtual cells, let multiple base stations to serve one car. Of course, there are multiple cars. So here I just chose one car, but in the reality, there are multiple cars, and each car will be supported by multiple base stations. So the main enabling technology here is called the vehicular edge network slicing. So how can we slice the resources? Here is the class association. So which cars you map into which group of the anchor points, and also how can we decide the wireless communication, like the beamforming scheme, and also the resource block, which slice should use which resource blocks. So that should be decided in a very large scale. And we use this distributed multi-agent reinforced learning to address this multi-dimensional network slicing. And some of our work also consider once you slice these resources, can you guarantee the hard deadline for the V2 infrastructure communications? And we have some of the publications you can see here. We try to use, here is like, yeah, I guess it's a Centennial campus at the NC State to mimic like the environments. And then we try to extract some of the information to see what's the performance for this network slicing. So that's the main ideas from 100 millisecond to 1 millisecond. We use a very simple open loop transmission, grain-free transmission. Then all the computations will be handled by the infrastructure, so that we can reduce the latency. So on the other hand, we also propose several intelligent OBU algorithms. Okay, so this one, so there are 2 or 3. So I just show some of the slide. If you are interested, feel free to follow our works. So the first one is, if our if there's a new user coming to the environments and there are already some existing V2X communication and the V2V communications, actually we can use the onboard computing capacity from the cars to perform these ultra broadband recognitions. Okay, so remember our SDVAC idea is put all the computations into the infrastructure. So in other words, that also help you can build some of your functions with this OBU. So this was just accepted by this InfoCon workshop. So we try to see if we have this very huge wideband available for our vehicle environments, how can we use machine learning to automatically recognize what are the existing usage and what are those patterns. So here shows that the original patterns and also our reconstruct patterns from our wireless sensing. And compared to the latest scan, we can get a better recognitions for the waveform, like 26% of performance scan, and with 56 less training overheads. So that's the first step. And once we can recognize the waveform from the device, like from a car perspective, we also propose this automatic modulation classification. That means you can let the receiver side autonomously reconfigure its front-end parameters to support the transmission. So of course, here we use the ResNet to help the designs for the receiver side. Okay, the receiver doesn't need any information from the transmitter. Once it receives the data or waveform, it can automatically recognize what's the modulation scheme and adjust its receiver. We also consider some of the practical case. If there is some frequency time phase offset, how can we adjust it? And we even consider whether these mechanisms can do the real time. So instead of real time learning, we install some real time inference rules into this SDR, the software defined radio, and we showcase this one into in 2019 in FRA, Beyond 5G SDR University showcase. So here is just some poster that I bring some of my students to the Air Force base, and then to actually it's like a White Brothers Institute. So we showcase that we can install the intelligence into the device, okay, using the FPGA capacities on this SDR to perform inference in the real time. Of course, we also consider if there are multi-antenna cases, whether we can perform this unsupervised learning to avoid the labeling efforts and then to even boost the real-time operations from this last mile transmission. Okay. So that's kind of like a quick summary about like the on-device computations we are working on. How about the upper layer communication? So as I mentioned, here this figure shows that each vehicles will be covered by multiple access points. For example, this orange car will be covered by this AP2, AP3, APN-1, and they have their dedicated resources usage sliced by each access points. Okay, and all the receptions will be collected by the local anchor nodes, and you can perform some of the smart intelligence. So in other words, for this network, it's like multi-pass and multi-hub communications, actually two-hub communications between the car to the infrastructure itself. So some of the conventional cooperative communication scheme can be operated here. So that's why we are saying, okay, for the last mile, we use open loop. So you just transmit grant free. As long as you have data, you just transmit. So all the operations or rectifications can be done by this infrastructure. And we have some of the work from the past that instead of address the last mile communications, actually we can use these multi-hub transmissions to address the communication and to support this error control on the anchor node side. Okay, so now we not consider the point-to-point transmission, but this is more like session level. You have a multi-hub transmission, and you have multi-pass receptions and anchor nodes. And actually, our previous work can be easily implemented into this network layer-wise error control. So on the other hand, we also try to set up, since we have multiple controllers like as the anchor nodes in the local end, how can we set up this multi-controller planning? So the idea is like given an infrastructure, we need to decided how many controllers do we need for this infrastructure. We need to decide where should this controller be located, and also the control domain assignments. That means the association or the relationship between the controller and the infrastructure devices. And lastly, we also need to consider how can we transmit this control message in a very short period of time from the controller to the switch. Okay, so here is for the control delay. Okay, should be much shorter than the delay we talk about, like the data transmission delay. So we all have this the designs that borrow from our previous work for the data center and the cellular network infrastructure. And one of the ideas to bring out from this edge computing or this vehicular edge computing is that we use this software-defined infrastructure to build up the entire infrastructure so that you can have the overview for the all types of resources. And with this infrastructure build up, actually, is for the first time, you can adjust all the resources to support the requirement. So what does that mean? The idea is that we can build up the intelligent network infrastructure that can manage all the resources. So not only the computation, but not only communications, but the computations or even data processing operations can be designed and to support the needed from these vehicular applications. So this work actually helped us to build up these orchestrations between the edge and the cloud, and is supported by the Cisco. And the idea is we try to implement these distributed TensorFlow platforms that we have actually two types of hierarchy. From the device, means the users can be the CAVs to the edge, and from edge to the cloud. How can we set up this parameter server and edge client to utilize the computation resources in both ends? And also we including this distributed data processing. The idea is that instead of using the raw data to train my machine learning models, I can actually perform some pre-processing to help or to even boost the machine learning techniques. So from these edge cloud orchestrations in our SDVAC environments, we try to perform two tasks. The first one is this edge caching and computations. How can we jointly optimize the service caching to the anchor nodes and task of loading to the cloud regarding this vehicular data and applications? In other words, we have the onboard device that have the computations. We have the edge node have the computations. We have the cloud servers have the computation capacities. How can we seamlessly schedule the tasks? For example, if there are two heavy tasks on the edge nodes, this edge node should automatically offload the computation to the cloud. Okay, so since we have this platform, SDN platform, we can do this hierarchical offloading scheme, and not only the data itself, but also the computation tasks can be offloading between this three-layer structure. Okay, so that's just a very brief deal. There are still so many details since we are trying to build up a new architectures that can work on this vehicular environment. So as I mentioned, if you are interested in some of the details, feel free to reach out to us. So for the next part, I will talk about some of our implementations. Okay, so we already introduced this SDVAC. So what's the current status about the experiment and test-bed implementations that we are working on? So as Ali mentions in the beginning of my talk, so my team did it by this. So my team is working on the Thrust2 for the NC-CAV, and this Thrust2 is led by the Thomas Chess, okay, the actually people at the NC State, and we mainly focus on how can we provide the visions for the next generation infrastructure paradigms. And the main focus, as you can see here, we use this SDVAC to support the low latency edge computing infrastructures for our next generation paradigms. And later on, we'll also consider about the safety issues with these paradigms. So in my lab, currently we try to we are implement these ideas from this, as I mentioned, the anchor nodes, the access points, and we use some of the devices to mimic like the users, like onboard sensors, and also the idea is how can you make sure there are multiple anchor nodes and you can still have a good overview pictures like coordinations between anchor nodes. In other words, in my lab, we have these fully functional prototypes, and we use some of the commercial off-the-shelf components like the Intel NUC or like TP-Links, even like some of the SDR to fabricate this entire infrastructure. So with 128 megabits data chunk and Hadoop applications, with these small scales, we can already show like there are 53% of reductions in the processing time if we operate on the local end instead of pushing all the data back to this cloud. Okay, so here we just have the two anchor nodes and we can already have this scan. So the other case is that we also trying to build up this simulation environment, or you can consider as a compact simulation tools for all our designs from the data plane, control plane, and also this network slicing tools. So we want it can be emulated through this through these sumo tools. So here shows that if we consider a real world vehicular environments, here is the figures from this downtown Raleigh, and we can use this sumo to acquire these informations and then play some of these transportation data to see what's happening. So currently, the basic function is we can do these traffic simulations to let the car running. Yeah, it's a little bit late, but the car can running on these given environments, and also we can have a different car running on the environments to show like the yellow one is the car and the blue one is the bus, and also we can have the control of the traffic light, and this, as you can see here, like depends on traffic light. This sumo can help us perform these emulations, and we can get this transportation data. So the most useful pieces here is given the same map or given the same transportation environments, we can randomly set up different trips within these same environments. As you can see, like the cars will have different paths given the same environments, and it really helps us to generate data for our Markov chain Monte Carlo simulations, because our idea is once we get these transportation informations, we will build up our own communication protocols, actually the computation-based protocols upon these transportation environments, and to see what's the results we can get and into for this real-world environment. Okay, yeah. So if you and that's kind of like the quick summary about from this SDVAC, we including this SDN ideas into the wireless, and also it integrated with the machine learning techniques, and how can we propose and or introduce this SDVAC and some of the functionalities and our current state-of-the-art implementations for this work. So our team is at NC State, and my team is mainly focused on its wireless communication and the networking areas, and this CAV work or like connected transportation is one of the main pieces in my team, and we have several PhD students that focus on different pieces, as we mentioned, like the SDN, and also you have this SDR, the wireless network and edge control, and even the development of the deep learning algorithms is also some of the capacities in my team. So not only that, we also see some of the into the future. So as I mentioned in the first couple of slides, the 6G actually brings out the case that not just the ICT development, but how can you bring this information communication technologies into different application scenarios. So that's why in my lab, we also consider different type of scenarios to realize these industrial verticals, such as one of our ideas is these SDR implementations. We can build up a reconfigurable RF front end so that it can dynamically access the spectrums. And also, how can these ideas can be built up with these UAV communications, as the beyond terrestrial communication is also a main important areas in the 6G. And the other idea is how can this infrastructure build up help the IoT case? Okay, and we have like two or three like use case. One is like we can help the smart agricultures to get more accurate information from wireless communications, and then have this edge computing node to produce a very high throughput phenotypes for the farmers. And I'll just use two of the case to show the other industrial verticals that are also working on in my lab. So the first one is, as I mentioned, this URAN. So if your like the UAV, if they can also carry on these access points, actually it's very similar to our SDVAC environments. We can also consider this UAV can set up mobile infrastructures for the given areas. So the idea is we can address the spectrum efficiency into the access network levels, and also in this case we also need to consider you need to have an energy efficient design. Okay, different from the SDVAC, like the anchor nodes can have the power line, right? But if you have this access point on the fly, you need to make sure the energy is enough for the UAV to operate its work. And our intention is that once we build up the entire algorithms and the solutions, we will integrate with this NSF airport. That is a very huge UAV platform at NC State, and we hope to see once our designs upon this platform, what's the actual performance we can get from there. Okay. The other one is just a brief ideas, like as I mentioned, we also trying to set up this computation-based edge network into the industrial environments. So the idea is how can we realize this industrial 4.0? They not only care about the connectivities, but also like autonomous controls can also be fulfilled there. So yeah, the other work you can, if you're interested, you can reach to us. So that's kind of the entire ideas I want to bring out today. And I want to recognize some of our supporters from like the NCDOT, especially for these projects, and also some from the FIO and Cisco. And of course, there are some internal supports of my work from the NC State. And that's all for today. And if you have any questions, I'm very happy to answer for it. Thank you.
Thank you so much. A very comprehensive review of so many things. I think it was very informative and eye-opening to so many ongoing things, and very interesting. Thank you so much. So go ahead. Somebody wanted to ask a question? I didn't.
The question.
Any question to Dr. Lin? Go ahead.
The question, if you have time, is that, like as Ali mentioned, there was a lot of content covered in a short period of time, so I didn't quite catch the part that you were saying about AI algorithms on, for the devices. What kind of AI have you were you considering, and what kind of data have you used, or what was the purpose of the?
Okay, yeah. So as I mentioned, we are building up the infrastructure. So actually, we cannot cover it in like an hour or 40 minutes. But the thing you ask actually is a very good question, because the AI and machine learning is the key point, as I mentioned, for the infrastructure build up. So we use it for the on-board communications. That means the onboard sensors and also these edge and cloud applications. And let me use this onboard device case as an example to answer your question. Second. So for this one, actually for this one, we use the sorry. Okay. So for this one, the structures we use is following the deep red snake. Okay. So we try to extend from the compressed sensing perspective. So the idea is that we have very huge wideband. So if we already know some ideas from these pass laws designs from the wireless communications, can that ideas bring into the machine learning designs? So of course, the idea is that we are not just inject the waveform into our machine learning, but with some model-based ideas, can these pass laws environments inject into the wideband learning so that it can perform the results. And the other idea is we actually let the radios to transmit to each other and to receive this waveform information. It's a real data. And then we run this, we try to see what's the results for this confusion map.
Sorry, along those lines, why did you use GAN then? I think I didn't understand.
No, we don't use GAN. The current standard we use GAN. We don't use GAN. Okay, the GAN is our comparisons. We use different GAN. So for this wireless part, we use the waveform. We first, of course, we first simulate the algorithms. Then later on, we use the real radio waveforms to validate our results. For the edge cloud orchestration one, we run several big data benchmark like the K-means or MINIST. So we try to see different big data benchmark, and if they happens to in our environments, how can we use Spark and TensorFlow to address that preprocessing? So in a short words, we use different types of machine learning mechanisms into the wireless communications and also infrastructures. It depends on which part we use, either like the real data from the wireless signals, or we use this image classifications or like pattern recognition data to train our model.
So, any other question? I have one question. I am from control background, and when we are solving a problem in control domain, there is a little bit background noise. I don't know. Is it?
Yeah, there's some noise in the background.
Yep. Okay. I think now it's better. So, yep. So we as a control engineers, when we try to solve a problem, we assume perfect communication, right? Yeah. So that's something that is happening. On the other hand,
sorry, I didn't.
You go back muted.
Okay. So
on the other hand,
yeah. On the other hand, the communication guys, when they try to solve a problem, right, you go with changing network topology is going to be assumed to be changed and is okay. So you can have different communication graph and so on, so forth, but you don't consider the significant impact of communication network on the performance on the control side as well. I understand these two approaches, because if we want to solve these two problems, control and communication, in a joint space, it would be quite complex problem. So that's why we try to solve these two problems in separate domains, but when we try to solve different domains, and communication, then we are doing a lot of simplification assumptions. And here also you were mentioning, okay, we're going to have the different the slicing of the network and so on and so forth, but actually those may impact the control. So what do you see as far as the impact of some decent strategies when they affect the control, and how is going to be the approach moving forward to address these challenges?
Yeah, actually, it's a very good question. And I think the reasons that we try to build up this computation-based platform is trying to consider the interactions between the communication infrastructure and the control infrastructure. Actually, the machine learning, some of the machine learning objectives can be the control mechanisms. If I want to provide the adaptive controls, how can that be performed? So one of the case maybe similar to what you mentioned is that if we want to set up multiple controllers, so sometimes we need to make sure the connection is good and also the controller can make consensus. So that's the pictures we will consider both the communications and the control function at the same time. And the conventional way is, as you mentioned, we will model some of the portions, maybe the perfect communication channels to address the control perspective, or we will use, we will consider communication models and with some Laplacian graph. Okay, so we will assume the convergence of the graph, and then we work on these communication problems. So that's because in that times we have this optimization as a tool, more like a model base. But nowadays, since we have these infrastructures, we can acquire all the informations. Actually, we try to perform, we try to use the machine learning or data-based solutions to see if we consider all the components, or we consider all the elements, what's the performance for the end-to-end part? So meaning the end-to-end learning part. So that's kind of the way we can address all the parameters at the same time, and we don't need to work on like multi-dimensional optimization. So I think that's of the kind of the way we are trying to work on. And from that's kind of the ideas. And the second part is like when we want to implement it, the good side is like I also have this capacity of these computer science tools. So one of the ideas is called the virtualizations. So the idea is since we have this very big chunk communication and control framework that needed to be solved by the machine learnings. Actually, if we have these virtualizations, we can slice. It's still like divide and conquer, but we can divide it in a nice way so that each tasks will only need to address their own portions. So I think that's kind of like two things we are working on. Like first, we have this big chunk. We can now use the machine learning, maybe like deep learnings to consider all the parameters and try to see what's the end-to-end learning performance, especially for control and communication KPI. And also we have these virtualizations trying to chop or divide and conquer the entire progress into pieces. And sometimes we will also borrow from the ideas of the model base, as I just explained, this ultra wideband. So it's not just purely install all the data into machine learning, but if you have some communications knowledge, you can help shrink the model or shrink the neural network structures. I think that will happen again. That will happen from a control perspective. If you have some control knowledge or insight, actually you don't need to have like full connected neural networks. You can do some notations to focus on specific structures. And yeah, that's kind of like the very brief answers to your questions.
Let me ask you a question. You assume an ideal world, basically. You didn't assume, or you didn't bring into the account communication latency and its impact in control. How do you address this?
Yeah. So here we try to reduce the communication latency. So the idea is that we try to provide a platform that can give a very short period of time. So our target is 1 millisecond. Okay, so that's still a very how can I say? very hard to reach. But our idea is with these architecture designs, we try to flatten the communication protocols so that we can help to provide end-to-end delay to a very small delay, like 1 millisecond, so that with this framework, if your control functions or applications sitting upon this infrastructure, it can utilize this 1 millisecond end-to-end delay.
Have you applied AADL to see whether you are satisfying communication requirement for the system?
Sorry, I didn't find you said the
it's called advanced architecture logic design, because it's a formal method to see whether you are satisfying the specification.
Yeah. So probably I haven't adopted the method you mentioned, but we follow the 3GPP spec. So the 3GPP spec, they have their standardizations for the 5G environment called the ORAN, Open RAN. So we are implementing their mechanism, like we are translating our designs into their spec. So in their spec, so that's why, as I mentioned, their spec consider the real-time, near real-time, and non-real-time components. So yeah, probably that's the one we are currently working on. And maybe I can ask you more, like you mentioned the conventional way, how can it test? Maybe we can also consider that as well.
Dr. Karimuddin's student Thaddeus is also here. He is basically one of the few students that we have. They check for these specifications whether the systems are satisfying or not.
From the industry perspective, or from the
from not the industry, from system level perspective.
Yeah, as I mentioned, when we fabricate this one, we are trying to see from like end-to-end communications. Yeah, but and the thing I mentioned is that that's our first step, right? So we also want this work can be promising to the industrial people. So we're also working with some companies to build up these 3GPP standards to make our work match to their work.
Great, thank you.
Thank you.
Hello, I have a question on slide number 29.
Yeah.
Can you go back one step? 29.
This is 29.
Okay, the one before this, 28.
This one?
Yeah.
This one or one before?
28. Slide number 28.
Yeah, this one is 28. One more? Okay.
Okay, yeah, this one. So here I think you used Resonate for this application. Usually Resonate is built for image classification, where you have image as input and labels for the image as output. So it's not clear for me what is the input for the model and what is the output.
So the input is so we want to recognize, so if the idea is we have the environment that many people are transmitting. So here shows like, so that's why the input is the combination signal waveform. Okay, so for example, if I have 3 users transmit at the same time, the figures or the input received is your sensing informations. You have the combined waveform. The output is each user's waveform. Okay, so I have these combinations, and I can let the machine learn by itself to partition or to recognize each user's waveform. So that's why here shows that 3 users, like each user, like sample 1, sample 2, sample 3, means their original waveform. Of course, original we don't know, right? Original is when we want to compare our results. So we want to compare our reconstruction waveform and the original waveform, and we want to see through our machine learning what's the mismatch there.
Okay.
So yeah, one of the peculiarity here is we can support a very huge range of the communication range. So that's why we call it terahertz. we try to model that from like a megahertz, megahertz to like terahertz. So all these very wideband, or we call ultra wideband communications, if there are some usage among this wideband, we can all recognize, or we can all extract from it.
Okay, so on the next page, slide number 29. Okay, here you also used a resonate, and I think here the input is kind of image, and the output is the type of the modulation.
Yes.
So this one is kind of different from the other one.
Similarly, so it's just, if you understand the digital communication, it's just different pieces. So for the receiver side, we first have the waveform, as I mentioned previously, right? So here, the input is the constellation map. It's still the one you receive, but like after the ADC, it means it's when you work on the baseband, you have this constellation map. Still, like the received signal you received, and you can automatically classify which modulation does it use.
Mm-hmm. So my other question is like such type of signals, they usually have some temporal dependencies inside them. And convolutional neural network is good for capturing spatial information. So like, have you considered to use time series algorithms such as recurrent neural network jointly with CNN to capture the temporal dependencies in the data as well?
Yeah, it's a very good question. So be careful here. We are not trying to invent the new machine learning algorithms. Okay, so we try to use it as a tool. And from your question, actually, it's a very good question. So I also work with the computer science people. So currently we are working on like the time-aware machine intelligence. So the idea is like, as you mentioned, these time correlations is hard to address. And for that work, we are currently consider from the architectural design perspective, if we have some nominal layer structures, can we extract the time correlations from there or not? Yeah, but for this work, we haven't considered the time correlations because our idea is if you can use by the military or like military purpose, they want you calculate it in a very short period of time. So of course you say like correlation can help, but the first step is how can you recognize in almost real-time second. So that's why we intend to reduce the computation load from that perspective.
Okay, okay,
Yeah.
Thank you.
But you asked a very good question. Actually, I just have my meeting with my PhD students the other day, and this time correlation will help a lot when we want to extend. Actually, it's the extension of this one. So we are currently working on the journal mergers. You have very good insight. So the idea is that if we have some information, since we are working on the sumo, right? So if we have some information from the roadside structure, or if we can inference the roadside structures, this time awareness actually help us. In a sense, if your users is now moving far away from the base stations, actually you don't need to revise the association parameters, or even like the physical layer doesn't need to change that much. So we are consider that components into the entire design as well.
Okay, all right. Thank you very much.
Okay, I think it's already taking a long thing, and I think if there is follow-up questions, still feel free to contact Dr. Lin later. I personally am interested in follow-up conversation, Dr. Lin, for two of the works. One is the one that Dr. Homaifar mentioned, the other one, a student of mine, Solomon, on swarm of SOAR, which I think the idea of the way that you do have a slicing a method for those communication network that you do have, and so whatever, it's going to be a nice integration might happen later. So I hope that we can have follow-up conversation later.
Yeah.
Okay. Great. Okay. Thank you so much, everybody, and have a great weekend.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye-bye.